Module 26. Lecture B. Density Anomalies. By the end of this lecture, you will be able to estimate densities using histograms and kernel density estimation, apply anomaly and novelty detection estimators to identify unusual samples, and use Bernoulli RBMs for simple binary feature representation learning. Density estimation. Histogram density. Histogram density estimation shows how data values are distributed by grouping them into bins and scaling the bars to reflect relative concentration. It helps reveal patterns such as clusters, symmetry, skewness, and rare values. In a hospital, for example, it can summarize patient waiting times and highlight unusually short or long delays that may need attention. In histogram density estimation, probability is represented by the area of each bar, so both height and bin width matter. Narrow bins can reveal fine patterns but may be noisy, while wide bins smooth the data but can hide important differences. The goal is to choose a bin width that balances detail with a reliable summary of the data. Histogram density estimation is a useful way to quickly explore how data is distributed before using more complex models. It can reveal common clusters, peaks, unusual values, and low-density areas that may indicate anomalies, such as rare pollution readings or unusual login activity. Its results depend on bin choices and can be harder to interpret in higher dimensions, but it remains a valuable tool for spotting patterns and outliers. Python code, histogram density. This example shows a density histogram, where each bar's area represents the probability within its bin. Values that occur rarely, especially near the edges, appear in low-density regions. We import NumPy to handle arrays and numerical calculations efficiently, and use Matplotlib's plotting tools to create graphs that help visualize and interpret data. A fixed random seed is used so the results can be reproduced. The data combines two simulated groups, 220 typical waiting times from a gamma distribution, and 8 unusually long waiting times from a normal distribution centered around 85. Together, they form one waiting time dataset for later analysis. The code first confirms that the waiting time data is a one-dimensional array, so it has the expected structure for analysis. If the data has the wrong shape, it raises an error. It also checks that the array contains at least one value, since an empty dataset cannot be analyzed meaningfully. To estimate the density of waiting times, first create evenly spaced bin edges from 0 to 110, giving 23 bins for the histogram. Then, use the histogram function to compute the bin densities and edges. Setting density to true normalizes the histogram, so its total area is 1, making it an estimate of the waiting time probability density. To check that a density histogram is properly normalized, first find each bin's width from the spacing between its edges. Then multiply each density height by its bin width to get the area for that bin, and add all the areas together. The total should be 1, or very close to 1, showing that the histogram represents a valid probability distribution. This example summarizes histogram density for hospital waiting times. It reports the total probability area by combining each density with its bin width, then rounding the result for readability. It also reports the smallest non-zero density, which shows the lowest observed density, while ignoring empty bins. This code creates a Matplotlib figure and axis, then plots a normalized histogram of waiting times using predefined bin edges. The histogram is styled with sky blue bars and black outlines, and its labels explain that the x-axis shows waiting time in minutes, while the y-axis shows estimated density. A clear title is added, and the plot is displayed to visualize the distribution of the data. This script simulates hospital waiting times by combining typical weights from a gamma distribution with a few longer weights from a normal distribution. It verifies the data, builds a density histogram from 0 to 110 minutes, and converts the bin densities into probability areas that sum to 1. It then reports the total probability area and the smallest non-empty density value before plotting the estimated waiting time density, showing where weights are more or less common. Kernel density. Kernel density estimation creates a smooth estimate of a probability distribution by placing a curve around each data point and combining them. Unlike histograms with fixed bins, it shows where values are common or rare across a continuous scale. This can reveal typical patterns, secondary patterns such as delivery delays, and anomalies that fall in low-density regions. In kernel density estimation, a kernel is a smooth curve placed around each data point to show its local influence. Nearby observations combine to create higher density peaks, while isolated values form small bumps or low-density tails. This makes the method useful for exploring patterns in data, such as identifying normal dense regions and sparse areas that may indicate anomalies. Kernel density estimation creates a smoother view of a distribution than a histogram, which can make trends easier to see. However, the result depends on the amount of data and the chosen level of smoothing, so a smooth curve is not automatically accurate. It is best interpreted alongside a histogram and domain knowledge. In settings such as medical screening, it can point out uncommon values, but uncommon does not necessarily mean abnormal. Python code. Kernel density. This example uses kernel density estimation to create a smooth one-dimensional view of delivery times. Unlike a histogram, it represents the density with smooth curves, making low-density regions easier to spot as possible unusual delivery times. We import NumPy for numerical work with arrays, and Matplotlib's plotting tools for creating visualizations. We also import Scikit-Learn's kernel density estimation tool to estimate probability densities, along with the main Scikit-Learn library for its machine learning utilities and version information. A fixed random seed of 42 is used so the simulated data is reproducible. The data includes 180 typical delivery times drawn from a normal distribution centered at 32 minutes with a standard deviation of 5, and 20 late delivery times centered at 55 minutes with a standard deviation of 3. We first combine the typical and late delivery times into one dataset, so all observed delivery times are analyzed together. Then we reshape the data into a single-column, two-dimensional format, because kernel density estimation expects each delivery time to appear as its own observation in that structure. Before estimating density, the delivery time data is checked to make sure it has the expected shape of 200 rows and 1 column. This confirms the data is in the right format for the kernel density function. If the shape is wrong, an error is raised to prevent problems during processing. We create a kernel density estimator with a Gaussian kernel to smooth the delivery time data. The bandwidth is set to 3, which controls how smooth the density curve is. After fitting the estimator to the observed delivery times, we can estimate the density at any point. To estimate density across possible delivery times, create a smooth set of time values from 10 to 70, and format it for the kernel density model. The model then scores each point to produce log density values, which are converted back into regular densities using the exponential function. The result is a smooth density curve for analysis or visualization. We evaluate 3 new delivery times, 30, 45, and 65 minutes, by formatting them as a column vector for the kernel density model. The model's score samples method gives the log density for each time, and exponentiating those values converts them into regular densities. These densities indicate how typical each delivery time appears, based on the data the model learned from. The process first checks the Scikit-Learn version to support compatibility and reproducibility. It then estimates how likely delivery times of 30, 45, and 65 minutes are under the model, by converting each log density into a regular density value and rounding the results for readability. Create a plot canvas with a figure and axis, then draw the kernel density estimate using the time grid on the horizontal axis and the density values on the vertical axis. Add the observed delivery times as a horizontal scatter plot at 0, using small, semi-transparent points so they do not overpower the density curve. Labels are included so the legend clearly distinguishes the density estimate from the observed deliveries. The plot is prepared with a clear title and axis labels to show a kernel density estimate of delivery times. The horizontal axis represents delivery time in minutes, while the vertical axis shows estimated density. A legend identifies the plotted elements, and the show function displays the final visualization for analysis. This script uses kernel density estimation to model delivery times as a smooth density curve instead of a histogram. It combines typical and late deliveries, fits the model, and shows where delivery times are common or unusual based on density. It also estimates how likely new delivery times of 30, 45, and 65 minutes are, and reports the Scikit-Learn version for reproducibility. Choosing bandwidth. In kernel density estimation, the bandwidth controls how smooth the estimated density curve is. A small bandwidth can make the curve too jagged and overly sensitive to random noise, while a large bandwidth can hide important patterns such as clusters or sharp changes. The goal is to choose a bandwidth that balances detail with stability, so the estimate reflects real structure without exaggerating random variation. Choosing a bandwidth in kernel density estimation requires balancing smoothness and detail. The best choice depends on the sample size, measurement scale, noise, and the goal of the analysis. If the bandwidth is too narrow, especially with small samples, random noise can look like real structure. If it is too wide, important patterns may be hidden. A good bandwidth filters out misleading artifacts while preserving patterns that are likely to generalize beyond the sample. Choosing bandwidth in practice combines software defaults with expert judgment. Defaults are useful starting points, but analysts should try several bandwidths to check whether important patterns remain stable. The choice should also match the data's units, since one bandwidth may not suit every variable. Careful bandwidth selection helps describe the data accurately and spot unusual observations. Python code. Choosing bandwidth. This example compares bandwidth choices in kernel density estimation. Bandwidth controls how smooth the estimated density appears, and different choices can lead to underfitting or overfitting. We import 3 key tools: NumPy for efficient numerical work with arrays, Matplotlib PyPlot for creating visualizations, and Scikit-Learn's kernel density estimator for estimating a random variable's probability density. We create a NumPy random number generator with a seed of 42, so the results are reproducible. This means the same random sequence appears each time the code runs, which helps with debugging and sharing consistent results. We simulate spending data by creating 2 random groups, low spenders centered around 35 and high spenders centered around 75. The low spending group has 80 samples, while the high spending group has 60. These groups are then combined into one dataset for later analysis. The code first validates that the spending data is a single numeric column, and contains at least 20 values. If the data is not in the expected format or is too small for meaningful analysis, it raises a value error. This early check helps prevent later processing problems. The code prepares the spending data for kernel density estimation by reshaping it into a single-column, two-dimensional format. It then creates a continuous range of spending values from 10 to 105, also in the required format. This range is used to evaluate and visualize the estimated density across possible spending amounts. Bandwidth values of 1, 5, and 15 are chosen to show different levels of smoothing in kernel density estimation. The smallest bandwidth produces a jagged estimate, the middle one gives a more balanced result, and the largest can oversmooth the data and hide detail. These labels help explain how bandwidth choice affects the final density estimate. We create a single figure with one set of axes using Matplotlib's subplots function, making it easier to compare different bandwidths in one clear plot. A 9 by 5 inch figure size gives enough room for detail without making the visualization too large. The code plots a histogram of the spending data to show its observed distribution. It uses 18 bins for detail and normalizes the bars so the total area equals 1, making the plot comparable to a probability density curve. The bars are gray and semi-transparent, with a legend label identifying them as the histogram. For each bandwidth, a Gaussian kernel density model is fitted to the spending data. The model then estimates densities across a grid of spending values, converting log density scores back to the normal scale. Each resulting density curve is plotted on the same axes and labeled by its bandwidth, making it easy to compare how bandwidth affects the estimate. The plot is labeled to make the kernel density estimation comparison clear. Its title identifies the focus as choosing bandwidth. The horizontal axis shows daily customer spending in dollars, and the vertical axis shows estimated density. A legend distinguishes the density curves for different bandwidth choices. Finally, the Matplotlib show function displays the completed plot. This lets us compare how different bandwidth choices affect the kernel density estimate, combining the histogram and density curves into one clear visual summary. This example shows how bandwidth affects kernel density estimation using simulated customer spending data with low and high spender groups. It compares density curves with small, medium, and large bandwidths against a histogram of the data. A very small bandwidth creates a jagged curve. A medium bandwidth captures the main structure well, and a very large bandwidth smooths away important detail. The key lesson is that bandwidth controls the bias and variance trade-off in density estimation. Anomaly detection, novelty versus outliers. In anomaly detection, outliers and novelty differ by when the unusual data appears. An outlier is an abnormal sample already present in the training data, so the model must handle training data that may not be fully clean. Novelty refers to new observations that appear after training on data assumed to be normal. This distinction shapes the assumptions we make about the data and how we interpret the model's alerts. Outlier detection assumes the training data may already contain unusual cases, so the model must learn the main pattern without letting those cases distort what counts as normal. It then flags observations that do not fit this core structure, such as faulty machine cycles in sensor data. Novelty detection is different, because the model is trained only on normal data, such as healthy machine cycles, and then checks whether new observations match that learned normal behavior. In this case, the quality of the normal training data is especially important. How we distinguish novelty from outliers affects how anomaly detection results are interpreted and used. Unusual cases are not automatically errors or fraud. They are signals that may need closer review. These systems act as screening tools that help prioritize investigation by defining normal behavior, choosing suitable training data, setting thresholds, and identifying meaningful deviations. 1 Class SVM. A 1 Class SVM detects unusual data by learning the boundary of normal behavior from training data that is mostly typical. Anything outside that boundary is treated as a possible anomaly or novelty. This is useful when abnormal examples are rare or hard to predict, such as in machine sensor monitoring or network traffic analysis. A 1 Class SVM learns a compact boundary around normal data, often in a richer feature space created with kernels. This lets it capture complex patterns of normal behavior, but the boundary must be tuned carefully. If it is too tight, normal cases may be marked as anomalies. If it is too loose, real anomalies may be missed. When using a 1 Class SVM, train it on data that truly represents normal behavior and contains as few real anomalies as possible. Scale features properly, so large numeric ranges do not distort similarity. This approach is best for moderate-sized datasets, and its results should be treated as signals for further investigation rather than final proof of anomalies. Python code, 1 Class SVM. This example trains a 1 Class SVM to learn what normal data looks like without using anomaly labels. It then predicts which points appear normal and which seem unusual. We import key Python libraries for anomaly detection: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning. From Scikit-Learn, we use the 1 Class support vector machine to learn the boundary of normal data, and the standard scaler to put features on a common scale so they contribute more evenly to the model. To make the example reproducible, we set up a NumPy random number generator with a fixed seed of 42. This ensures the same random sequence is produced each time the code runs, which is important when demonstrating or testing machine learning models. We create training data to represent normal behavior by generating 162 feature points from a normal distribution centered at 0 with a standard deviation of 0.7. This gives the model typical examples to learn as normal. The test data is built by combining normal points with clear anomalies. The normal set contains 62 dimensional points drawn from a normal distribution centered at 0 with a standard deviation of 0.7. The anomaly set contains 12 two-dimensional points drawn uniformly between 3 and 5. These two groups are then stacked into one dataset to test whether the model can separate typical points from unusual ones. Before modeling, the code verifies that both the training and test data contain exactly two numeric features. This check is needed because the lesson is built for two-dimensional data. If the data does not match this format, the code raises an error, so the problem can be fixed before later steps. We scale the features so they have equal influence on the 1 Class SVM. A standard scaler is fitted only on the normal training data to learn the mean and standard deviation. Then the same scaling is applied to both training and test data. This keeps the datasets consistent and helps the model work properly with features on similar scales. A 1 Class support vector machine is set up for anomaly detection and trained on scaled data. It uses a radial basis function kernel to model complex patterns, with gamma adjusted automatically based on the data features. The new setting of 0.08 tells the model to expect a small share of anomalies as it learns the boundary between normal points and unusual ones. The model predicts whether each scaled test point is normal or unusual. Normal points are labeled as 1, while unusual points are labeled as -1. By counting these labels, we get the total number of predicted normal points and anomalies. The code reports the Scikit-Learn version to support compatibility and reproducibility. It then shows how many test samples the model classified as normal and how many it flagged as unusual, giving a quick summary of the model's anomaly detection results. To visualize what the model has learned, we create a grid of points covering the input space from -3 to 5.5 in both directions. The grid is built by combining evenly spaced x and y values, then turning those combinations into coordinate pairs. Evaluating the model across these points lets us see the decision boundary between normal and unusual data. The grid points are first scaled to match the feature space used during training, so the model can make consistent predictions. The model's decision function then measures how far each scaled point is from the learned boundary and reshapes the results to fit the grid. Positive values mark points inside the boundary, showing the region the model considers normal. A plot is set up with a figure and axis. Then the contour method is used to show the one Class SVM decision boundary. The boundary is drawn at level 0, marking the separation between normal and unusual points, with a clear black line. The normal training data is then added as small scatter points and labeled so it can be distinguished in the visualization. We separate the model's test predictions into normal points and unusual points, based on whether each prediction marks the data as normal or anomalous. Then we create a scatter plot for each group, using different point sizes and labels to distinguish them. This makes it easier to see how the model separates normal data from unusual data. The visualization is labeled to show it presents one Class SVM anomaly detection, with the two axes named Feature 1 and Feature 2. A legend helps distinguish the training data from predicted anomalies, and the plot is then displayed using Matplotlib's show function. This script shows how a one-class support vector machine can detect anomalies. It trains on scaled normal data to learn the boundary of typical behavior, then tests new points that include both normal samples and outliers. The model labels each test point as normal or unusual, reports the counts, and uses a plot to show the predictions and decision boundary. Isolation forest. Isolation forest detects anomalies by measuring how quickly data points can be separated through random splits. Unusual points in sparse areas are isolated faster, while normal points in dense groups require more splits. This makes it useful for finding rare or unexpected cases without building a detailed model of normal behavior. Isolation forest detects anomalies by building many random isolation trees and combining their results. Each tree randomly splits the data until samples are separated, and the key signal is how many splits are needed. Samples with shorter path lengths are easier to isolate, so they are more likely to be unusual, such as a machine sensor showing unusually high vibration. Isolation forest is efficient for large, complex datasets because it detects unusual points without estimating regional density. It is used in areas such as cybersecurity, finance, healthcare, and manufacturing to flag patterns that may signal problems like fraud or equipment failure. However, an anomaly score only means something is unusual, not necessarily harmful, so results must be interpreted carefully. Performance depends on representative normal training data, useful features, and an appropriate detection threshold. Python code, isolation forest. This example shows how isolation forest detects anomalies in simple two-dimensional data. By using random splits, the method tends to isolate unusual points faster than typical points, and the predicted anomalies are marked in red. We import key Python libraries for the anomaly detection task: NumPy for efficient numerical work, Matplotlib for plotting data and results, and Scikit-Learn for machine learning tools. From Scikit-Learn, we use the isolation forest algorithm, which detects anomalies by isolating outliers in the data. A fixed random seed of 42 is used so the results can be reproduced. The generator then creates 180 two-dimensional data points from a normal distribution centered at 0, with a standard deviation of 0.7, producing a compact cluster. Anomaly points are created as two-dimensional coordinates placed far from the main data cluster. These points are then combined with the normal points using NumPy's vertical stacking function to form one dataset. The resulting data includes both typical observations and outliers, making it ready for analysis with an isolation forest model. Before modeling, the code verifies that the dataset has 184 rows and 2 columns. If the dimensions are different, it stops with an error message. This quick validation helps ensure the data is properly structured and prevents problems during model training. An isolation forest model is created with a 4% contamination level, meaning it expects about 4% of the data to be anomalies. A fixed random state makes the results reproducible. After the model learns the normal patterns in the dataset, it labels each point as normal or anomalous, highlighting the points that differ most from the expected behavior. The code turns isolation forest predictions into simple Boolean masks. Negative labels mark anomalies, while positive labels mark normal data points. This makes it easier to filter and visualize the two groups separately. The code reports the Scikit-Learn version to support compatibility and reproducibility, then counts how many samples were flagged as anomalies. It also notes that lower model scores mean a sample is more unusual, which helps interpret the anomaly detection results. Create a Matplotlib plot with a chosen size. Then use the axis scatter method to show two groups of points. Normal points are plotted with partial transparency and labeled as predicted normal, while anomalous points are plotted in red with a larger size, so they stand out as predicted anomalies. The plot is finalized by adding a clear title for isolation forest anomaly detection and labeling the two axes as Feature 1 and Feature 2. A legend is included to distinguish normal points from anomalies, and the Matplotlib show function displays the visualization so the model's results can be interpreted visually. This example uses an isolation forest to detect anomalies in a simple two-dimensional dataset. It creates mostly normal clustered points with a few outliers. It trains the model with a 4% contamination setting and reports how many samples are flagged as unusual. A scatter plot then highlights normal points and red anomalies, showing how the model separates typical data from isolated outliers. Bernoulli RBM features. Local Outlier Factor. Local Outlier Factor detects unusual observations by comparing a point's local density with that of its nearby neighbors, rather than measuring distance from the overall center of the data. This makes it useful when data contains different kinds of clusters, because a point is judged against similar nearby points instead of the whole dataset. In binary feature settings, such as features from a Bernoulli Restricted Boltzmann machine, it flags samples whose feature combinations are unusual within their local neighborhood. Local Outlier Factor detects outliers by comparing how dense a point's nearby area is with the density around its neighbors. For binary data, such as symptoms or permissions, it can find profiles that are unusual because their combination of features is rare among similar cases. This makes it useful for spotting local, context-dependent anomalies rather than only globally extreme values. Local Outlier Factor can detect anomalies using features learned by a Bernoulli Restricted Boltzmann machine, but its success depends on the quality of those features. The model turns binary data into compact patterns, then compares local neighborhoods to find samples that look unusual. Because results depend on choices like neighborhood size and distance measure, a high outlier score should be treated as a signal for further investigation, not proof. Domain knowledge and visualization can help interpret the findings more reliably. Python code, local outlier factor. This example shows how to detect local density anomalies using binary features that resemble learned RBM activations. It identifies samples that are unusual compared with their nearby neighbors. We import key Python libraries for numerical work, visualization, and anomaly detection. NumPy supports array operations and random number generation, while Matplotlib helps create plots and charts. Scikit-Learn provides the local outlier factor method for finding unusual data points based on local density, along with access to broader machine learning utilities and version information. 2 binary activation clusters are generated with a fixed random seed, so the results are reproducible. Each cluster has 45 samples and 4 features, with cluster A making the first 2 features likely to be active and the last 2 unlikely. Cluster B uses the opposite pattern, making the first 2 features unlikely and the last 2 likely. Together, these clusters model common binary activation patterns in learned representations. Rare binary patterns are added to the existing common pattern groups to create one combined feature set. The samples are then labeled, so the common patterns are marked as common, and the 3 rare patterns are marked as unusual. This prepares the data for testing whether a model can correctly identify unusual samples. The code verifies that the feature matrix has 93 rows and 4 columns, matching the expected samples and features. If the dimensions are different, it raises an error, so later analysis does not run on incorrectly shaped data. A local outlier factor model is set up to detect unusual samples by comparing each point with its 10 nearest neighbors, and assuming about 8% of the data may be outliers. After fitting the model to the feature data, it labels each sample as either typical or unusual. The model's outlier scores are then converted so that higher values indicate samples that differ more strongly from their local neighbors. To make 4 binary features easier to interpret, we reduce them to 2 coordinates. The first coordinate counts active features in the first group, and the second counts active features in the second group. This 2-dimensional view makes patterns and anomalies easier to see. The process identifies the 5 most unusual samples by sorting their outlier scores from highest to lowest. It also reports the Scikit-Learn version for reproducibility, and notes that higher local outlier factor scores mean a sample is more locally unusual. The results include the top sample indices, their rounded scores, and how many of the 3 known rare samples were correctly flagged as outliers. We first set up a plotting canvas with Matplotlib, then create 2 masks based on the model's predictions. One mask selects samples predicted as normal, and the other selects samples flagged as outliers. These masks let us separate the 2 groups clearly when visualizing the local outlier factor results. The code visualizes local outlier factor results for binary feature activations using a scatter plot. Normal samples are shown in blue, while detected outliers are shown in red. The plot includes a title, axis labels for the active feature counts in 2 groups, and a legend, so the viewer can quickly interpret which points are normal and which are anomalies. This script uses the local outlier factor algorithm to find anomalies in binary feature data that simulates learned activations. It creates common pattern clusters along with a few rare samples, then flags likely outliers using an 8% contamination setting. The results rank the most unusual samples and show how many known rare cases were detected. A simple plot separates normal samples from outliers, making the difference between common and anomalous patterns easier to see. Elliptic envelope. The elliptic envelope detects anomalies by assuming normal data forms one compact elliptical cluster. It estimates the center and spread of that cluster, then flags points far outside the boundary as unusual. This method works best for continuous data with a clear central pattern, such as stable measurements or typical transactions. An elliptic envelope works best when the data form one main group and the relationships between features are roughly Gaussian. It detects anomalies by looking for unusual combinations of features, even when each feature alone appears normal. For example, engine temperature, vibration, and pressure may follow a shared pattern, and readings that break that pattern can be flagged. The method is less reliable for curved patterns, multiple clusters, non-Gaussian data, or categorical and binary variables. In binary feature learning, a Bernoulli Restricted Boltzmann machine can first compress raw binary data into meaningful hidden features, such as patterns in user preferences or purchases. An elliptic envelope can then model what is normal in this feature space and flag samples that deviate from it. This creates a simple anomaly detection workflow. Learn the important structure first, then identify observations that fall outside the expected pattern. Python code. Elliptic envelope. This example finds unusual binary patterns by first using an RBM to compress them into learned hidden features. An elliptic envelope then identifies samples that fall outside the normal feature cloud. We import key Python libraries for numerical work, visualization, and machine learning. NumPy handles arrays and calculations, Matplotlib supports plotting, and Scikit-Learn provides the machine learning tools. From Scikit-Learn, we use a Bernoulli Restricted Boltzmann machine to learn binary features and an elliptic envelope model to detect outliers. A fixed random seed of 42 is used so the synthetic data can be reproduced. The generator then creates 180 normal profile samples, each with 12 binary features, using a binomial process, where each feature has a probability of 0.25 of being 1. This produces a consistent dataset for later analysis. Anomaly profiles are created by generating binary feature samples with a high chance of activation, making them unusual compared with normal profiles. These atypical profiles are then combined with the normal ones into a single dataset. The model uses this combined data to learn typical patterns and identify anomalies. We first use NumPy's unique values function to confirm that the binary profiles contain only zeros and ones. If any other value appears, an error is raised because the feature matrix must be strictly binary. This validation protects the integrity of later processing steps that depend on binary input. A Bernoulli Restricted Boltzmann machine is initialized to learn 2 hidden binary features from the input data. It is trained with a learning rate of 0.05 for 20 passes through the data, with a fixed random state to make the results reproducible. The trained model then transforms the binary input profiles into a smaller feature representation that captures their main patterns. An elliptic envelope model is used to detect outliers by fitting an elliptical boundary around the main cluster of data. It assumes about 10% of the samples may be anomalies, and a fixed random state makes the results reproducible. The model is then applied to the features learned by the restricted Boltzmann machine, labeling each sample as either inside the boundary or a potential outlier. To count anomalies, first identify the samples whose predicted label is -1, meaning they fall outside the learned envelope. Then, count how many samples meet that condition and convert the result to an integer for a clear anomaly total. The code reports key checks from the workflow: the scikit-learn version for reproducibility, the shape of the features learned by the restricted Boltzmann machine to show the transformed data size, and the number of samples flagged as anomalies by the elliptic envelope. A Matplotlib plot is created to visualize RBM-learned features using an elliptic envelope anomaly detector. Normal points are shown as inside the envelope with moderate transparency, while flagged anomalies are plotted separately with higher visibility. The title identifies the plot as showing how the elliptic envelope separates anomalies in the reduced RBM feature space. The plot labels the horizontal axis as the first RBM hidden feature, and the vertical axis as the second. A legend separates normal points from anomalies, and the plot is then displayed so the feature distribution and flagged outliers can be inspected visually. This script demonstrates anomaly detection on synthetic binary data using a Bernoulli Restricted Boltzmann machine and an elliptic envelope. The RBM reduces the data into two hidden features, and the elliptic envelope flags points that fall outside the main feature cluster as anomalies. The output reports basic run information and the number of detected anomalies, while a plot shows the normal feature cloud and the highlighted outliers. Bernoulli RBM. A Bernoulli Restricted Boltzmann Machine, or RBM, learns patterns in binary data, where each feature is treated as on or off. It uses a visible layer for the input and a hidden layer to capture relationships between features, with connections only between the two layers. This structure makes training simpler, while allowing the model to discover useful patterns, such as common shapes in binary image data, without being explicitly told what to look for. A Bernoulli RBM learns a compact representation of binary input data by using hidden units to detect recurring patterns in the visible units. These hidden units turn many low-level signals, such as purchases or symptoms, into a smaller set of meaningful features, such as shopping themes or common medical profiles. These learned features can then improve tasks like classification or anomaly detection. Bernoulli RBMs can detect unusual binary patterns by learning what normal data looks like and flagging patterns that do not fit. In cybersecurity, this can help identify suspicious user behavior based on common actions, such as logins or downloads. They work best when the binary features are meaningful and the training data represents normal behavior, though they do not explain anomalies in human terms. Python code. Bernoulli RBM. A Bernoulli Restricted Boltzmann machine can learn binary features from digit images. Its hidden units capture recurring pixel patterns, forming feature templates that resemble parts of digits. We begin by importing the main tools for the demonstration: NumPy for numerical array operations, Matplotlib for visualizing results, and Scikit-Learn for machine learning. From Scikit-Learn, we use a Bernoulli Restricted Boltzmann machine to learn binary features, along with the digits dataset of small handwritten digit images, to show how the model can detect patterns in binary data. We begin by loading Scikit-Learn's small digit image dataset, a useful example for working with binary features. The image data is then taken from the dataset and used to show how grayscale pixel values can be converted into binary features for training a restricted Boltzmann machine. Before reshaping the image data, we verify that each image has the expected 8x8 size. If an image does not match, an error is raised to flag the problem. This check helps ensure the data is in the right format and prevents issues later in processing. The code prepares the images for a Bernoulli Restricted Boltzmann machine by flattening each image into a row of pixel values. It then converts the grayscale values into binary features using a threshold. Pixels above 8 become 1, and the rest become 0. This lets the model learn patterns from binary input data. A Bernoulli Restricted Boltzmann Machine is set up to learn 16 binary hidden features from binary pixel data. It trains for 20 passes with a learning rate of 0.05, while a fixed random seed makes the results reproducible. During training, the model adjusts its weights to capture patterns and structure in the input images. The first 5 binary pixel examples are converted into hidden feature probabilities using the Bernoulli RBM transform method. Then, the average activation of each hidden feature is calculated across those examples, showing how often each learned feature is active in the input samples. The output summarizes key details of the restricted Boltzmann machine setup and results. It reports the Scikit-Learn version for reproducibility, the number of pixel-based input features per image, and the number of hidden features learned by the model. It also shows the average activation of the first 5 hidden features, giving a quick sense of how strongly those learned features respond across the initial samples. The RBM's learned components are reorganized so they can be viewed as one coherent image. First, the feature templates are arranged into a grid that matches the original image structure. Then the grid axes are transposed to align the features correctly. The result is reshaped into a single 32 by 32 matrix, making the learned patterns easier to display and interpret. This visualization creates a square plotting area and displays the Bernoulli RBM's learned feature templates as a grayscale image with reversed intensity. The plot is titled to identify the templates, and both axes are labeled as visible pixel positions across templates. Tick marks are removed to keep the view clean, and the plot is then shown so the learned patterns can be inspected visually. This script trains a Bernoulli Restricted Boltzmann machine to learn binary patterns from digit images. It converts the images into on or off pixel features, trains a model with 16 hidden units, and uses it to estimate hidden feature activations for a few examples. It then displays the learned feature templates, showing the recurring digit-like pixel patterns captured by the model. In this lecture, you learn to estimate densities using histograms and kernel density estimation, apply anomaly and novelty detection estimators to identify unusual samples, and use Bernoulli RBMs for simple binary feature representation learning. In the next module, Module 27, we will go over cross-validation.
Thank you for your attention. See you all in the next lecture.